In the last lecture, we were discussing the flow around a spherical particle. The parameters here are the diameter of the particle, the free stream velocity, which is the velocity, constant fluid velocity far upstream of the particle, and the density and the viscosity, of course. And there is one dimensionless group that can be made, which is the Reynolds number, rho v free stream diameter divided by the viscosity. In the limit of low Reynolds number, when it is less than about 1.5, the flow is symmetric between the upstream and the downstream hemispheres. Okay. And in this case, we can use Stokes' drag law for the drag force. If you recall, Stokes' drag law was that the drag force is equal to 3 pi mu d VFS. Okay. 3 pi mu d into V is Stokes' drag law at low Reynolds number. And based upon that, you will get the drag coefficient as 24 by Re, okay, where the drag coefficient, you recall, was defined as Fd by the projected area pi d square by 4 divided by half rho times the VFS square. Okay, so when the Reynolds number increases beyond about 1.5 and it is less than 24 or so, there is no symmetry between the upstream and the downstream directions. Okay. And so the downstream side, the streamlines converge much more slowly than the divergence on the upstream side. So it is asymmetric, and inertial effects are important. If inertial effects are not important, it will be symmetric. The drag coefficient has a correction due to inertia, okay, 24 by Re into 1 plus 0.15 Re power 0.687. Between 24 and 400, there is the formation of a separation bubble on the rear side. That is, the fluid that is coming in from far upstream does not go all the way around to the downstream side of the sphere, but rather it goes around what is called a separation bubble. Within the separation bubble, there is recirculation of the same fluid within that bubble. Okay. And in this case as well, this correlation, the Shiller-Naumann correlation that I had earlier, this same correlation applies for this as well. Okay. Between about 400 and 4000, you have periodic what is called vortex shedding. Okay. In the wakes, you have shedding first of the vortex on the upper hemisphere and then on the lower hemisphere in an alternate fashion. The flow is no longer steady. Okay, and you have this wake vortex shedding. When the Reynolds number is between 4000 and 2 into 10 power 5, you have turbulence in the wake. Okay, the periodic shedding gives rise to turbulence, which is chaotic velocity fluctuations in the wake region. The drag coefficient in this region is very close to 0.4. It is almost a constant, as you would expect in the high Reynolds number limit, where inertia is no longer a parameter. I am sorry, where inertia is the only parameter. High Reynolds number, inertia is much larger than viscosity. Inertia is the only parameter. Viscosity is not important, and therefore from dimensional analysis you will find that the drag coefficient has to be a constant. And at 4 into 10 power 5, you have a transition to what is called a drag crisis. There is a shift in the downstream direction of these points, of these attachment points of the wake, and the upstream portion of the sphere also becomes turbulent. Okay. That is what is called the drag crisis. Okay. And so these we had drawn on a plot of log of CD versus log of Re. Okay. The different transitions at the different Reynolds numbers and the expressions for the drag coefficient in each of these regions. Okay. So first you have 24 by Re when the Reynolds number is less than about 1.5. In this region you have CD is equal to 24 by Re into 1 plus 0.687. Okay. Here CD is equal to 0.4. Okay. and then the drag crisis takes place. Okay. So, this is the sequence of flow patterns and the drag coefficient or the drag force on the sphere. Okay. Let us now examine, for a realistic system, what will be the size and the velocity at which these transitions take place. Okay. What will be the size and the velocity at which these transitions takes place. Okay. So, consider a particle of mass density 1000 kg per meter cubed, settling in a fluid, okay, which is air. So, let us just call that as air, with mass density 1.25 kg per meter cubed and viscosity 1.8 into 10 power minus 5 kg per meter per second. Okay. So, estimate, okay, the diameter and terminal velocity for RE is equal to 1.5, 24, 400, 4000, 2 into 10 power 5. Okay. That is the diameter and the velocity, terminal velocity of the particle at each of these transitions, okay, between different kinds of flow patterns. Okay, what is the actual size of the particle at which you will see these kinds of different kinds of flow behavior. Okay. So, how do we calculate this? Okay. First of all, we have to estimate what is the terminal velocity. Okay. The terminal velocity is determined by a balance between the drag force and the gravitational force. Okay. That is, Fd will be equal to a mass times the gravitational acceleration. Okay. The gravitational acceleration, when expressed in terms of the particle diameter and the mass density, is equal to pi by 6 d cubed times rho p, volume of the sphere times the density into the gravitational acceleration. Okay. That is the drag coefficient. I am sorry, that is the drag force. The drag force has to be equal to the gravitational force. Note that in this case I am neglecting the effects of buoyancy. Okay. The reason is because the density of the particle is 1000, whereas the density of the gas is just 1.25. So, the particle is about 800 times more dense than the gas. Okay. So, I am neglecting the density of the gas and the buoyancy due to the presence of the gas. So, for the settling velocity, Fd has to be equal to mg. Okay. What should be the drag coefficient at Fd? Okay. Cd is equal to Fd by pi d square by 4, okay, divided by, in this case, the free stream velocity is the relative velocity between the particle and the fluid far from the particle. Okay. In this case, we are considering a particle that is settling relative to the fluid. So, the free stream velocity is the relative velocity between the particle and the fluid far from the particle. So, if we assume that the air is stationary and the particle is settling at its terminal velocity, that free stream velocity is just the terminal velocity of the particle. Okay. So, this rho V terminal square by 2. Okay, and I have to substitute the drag force here. Okay, so this will be pi d cubed by 6 rho p g divided by pi d square by 4 divided by rho v free stream square by 2. Okay. And you can do this calculation. Okay, simplify, you will get 4 rho p g d by 3 rho f times v t square. Okay. Note that v square by root g d is the Froude number. So, this is 1 over the Froude number squared times the density ratio. Okay. And if I put in the numbers, I will get this is equal to 4 into 10 power 3 kg per meter cubed into d into g will be 10 meters per second square divided by 3 into 1.25 into 1.25 kg per meter cubed into Vt square. Okay. And this I am getting as 1.07 into 10 power 4 meters per second square into d by Vt square. That is the drag coefficient. Okay, that is the drag coefficient in terms of the diameter and the terminal velocity. Okay. What is the Reynolds number? Rho Vt d by mu. Okay. This is 1.25 kg per meter cubed into Vt into d which turns out to be 6.94 into 10 power 4 meters per minus 2 second into Vt into d. Okay. Okay, the Reynolds number is proportional to the terminal velocity times d. Okay. So, there is the drag coefficient and the Reynolds number. Okay. So, now I can get the velocity and the diameter in terms of the drag coefficient and the Reynolds number. Okay. You can see that the drag coefficient goes as 1 over velocity square, Reynolds number is proportional to velocity. Therefore, C d into Reynolds number square is equal to 5.14 into 10 power minus 13. 10 power 13, sorry. Okay. Into d square. Okay. And in order to get the velocity, I can just get Re by Cd. Okay. Once again, if I multiply, take the ratio of these two. Okay. The diameter will cancel out and I will get only the velocity cubed, okay, because I have a velocity here and I have velocity 1 over velocity square there. Okay. So, this will be 6.51 into meter per minus 3 second per 3 into Vt square. Okay. Note that these prefactors have dimensions such that the product of these and diameter square, okay, I am sorry, this should be d cubed. Okay. Because if I take C d times R e square, I will get a d from the C d and a d square from the RE square. Okay. These prefactors ensure that the total product is dimensionless, as they should be, because you have only dimensionless parameters on the left hand side. Okay. So, now that I have these, I can calculate, okay, CD and RE, substitute that to get diameter cubed and velocity. Okay. So, first thing I would take is the Reynolds number at the different values, okay, 1.5. Okay. The correlation CD is equal to 24 by RE. Okay. This gives me a CD of 15, of 16. Okay. And the diameter is 8.88 into 10 power minus 5, this diameter in meters, and the terminal velocity in meters per second is 0.24. Okay. So, particles less than 8 into 10 power minus 5, okay, 10 power minus 6 is a micron, 10 power minus 3 is a millimeter. Okay. So, 10 power minus 5 is approximately 0.1 millimeters, okay. Less than about 0.1 millimeters settling in air is in the laminar regime, okay, where the Stokes drag coefficient applies. Okay. These particles have a velocity of approximately 0.25 meters per second. Okay. So, it is for these small particles which are less than about 0.1 millimeters and of in diameter, and the velocity is about 0.25 meters per second, the flow is laminar. Okay. Between 1.5 and 24, I can use the modified drag coefficient okay. So, for RE is equal to 24, I can calculate this. The drag coefficient turns out to be 2.33. Okay. And using these two relations, CD into RE square and RE by CD, I can calculate the diameter and the terminal velocity. So, this diameter turns out to be 2.97 into 10 power minus 4 meters. Okay. It is about 0.3 millimeters, okay, less than about 0.3 millimeters, you have a separation bubble at the rear, and the velocity is about 1.17 meters per second. Okay. The next transition is about 400. Okay. Note that at this also this same drag coefficient applies. Okay. The Schiller-Naumann correlation applies up to about 400, okay, if you recall. Okay. Up to about 400 is where the Schiller-Naumann correlation applies, okay, in this region. And you can calculate the drag coefficient is about 0.61. The diameter is 1.24 into 10 power minus 3, okay, 1.25 millimeters. At this point, the Reynolds number is about 400. Okay. And the velocity in this case is about 4.65 meters per second. Okay. The next is 4000. We know that at this point the drag coefficient is 0.4. Okay. Okay. The particle diameter, if you calculate it using this Reynolds number and this drag coefficient, turns out to be about 4.99 into 10 power minus 3 meters, about half a centimeter. Half a centimeter particles have Reynolds number of about 4000 and the drag coefficient is saturated about 0.41. Okay. The velocity is 11.54 meters per second. Okay. And the drag crisis takes place at 2 into 10 power 5. Drag coefficient at this point is also 0.4, just before the drag force decreases. Okay. So, this is 0.4 and the particle is about more than 6 centimeters, 6 centimeters, 6 to 7 centimeters in diameter. Okay. At that point you get the drag crisis and the terminal velocity is about 42.51 meters per second. Okay. So, this gives you roughly the ranges of diameters and terminal velocities for which we see these different kinds of behavior, okay, in this system. Okay. The diameter range from about 10 microns, I am sorry, 0.1 10 power minus 4 meters is about 0.1 millimeter. Below that it is viscous, okay. The velocity is less than quarter meter per second, all the way to greater than 7 centimeters, and the velocity is of the order of 40 meters per second. Okay. So, this gives you a physical idea of what are the ranges of particle diameters for which you are going to see different kinds of behavior. Okay. So, that is as far as flow around a particle is concerned. The next topic is flow around a bubble. Okay. So, bubble, the difference between a bubble and a particle is that for a particle the velocity, if the particle is stationary, the velocity has to decrease to 0 at the surface. Okay. There is a no slip condition at the surface for a fluid that is flowing past a particle. Okay. There is a no slip condition at the surface, that is, the fluid velocity has to be equal to the particle velocity at the surface. If you are in a reference frame moving with the particle, the fluid velocity has to decrease to 0 at the surface. Okay. And it is because of this no slip condition that you get the separation bubble, the formation of wakes and so on at the rear. Okay. So, this is for a solid particle. Okay. On the other hand, for a gas bubble, okay, you have a 0 shear stress condition at the surface, as I had discussed earlier. Okay. The velocity does not decrease to 0. Okay, that is because the what is inside the bubble is the gas, and the gas has a very small viscosity compared to the fluid. Okay, and because of that the shear stress in the fluid has to decrease to 0 as you approach the surface of the bubble. So, there is the no slip condition does not apply here. The no slip condition applies at a solid surface, because the solid cannot be deformed, okay, if it is a rigid solid. A bubble, you can generate internal flow, okay, and the viscosity of the bubble is very small. So, you apply a 0 shear stress condition at the surface, okay, and that is the fundamental difference between particles and bubbles. I should note that this 0 shear stress conditions only applies under specific conditions where there are no surfactants or anything on the surface of the bubble. Okay. So, that there is nothing that is resisting the non-zero velocity at the interface. If you have a dirty liquid in which there are surfactants or some other surface active materials which accumulate at the surface, okay, here are some surface active materials which accumulate at the surface. In that case, if you apply a flow, these materials will also have to move, and they will resist motion, and therefore, you will have a no slip condition at the surface. Okay. So, the 0 stress condition applies only under very specific conditions when the fluid is completely clean with no surfactants and so on. Okay. And when that is true, okay, you do not have the characteristics that we saw for the flow past a particle. Okay. You do not have the formation of separation bubble, the wake is negligible in thickness, there is no vortex shedding, and there is no boundary layer separation and so on. Okay. So, because of that, even at high Reynolds number, there is inertial domination of the flow, but the flow still looks symmetric between the upstream and the downstream hemispheres, okay, for the flow past a gas bubble. Okay. And the drag coefficient for the flow past a gas bubble at low Reynolds number, CD is equal to 16 by Re. Okay. Note that it was 24 by Re for the flow past a particle at low Reynolds number. In this case, it is less, because the boundary condition on the surface of the bubble is the free slip condition, the 0 shear stress condition. Okay. And at high Re, for very clean fluids with no surfactants in it, okay, the correlation for the drag coefficient is 48 by Re. So, the drag coefficient is proportional to 1 over Re for both low Reynolds number and high Reynolds number for the flow past a bubble. In the case of flow past a particle, we saw that it was 1 over Re for low Reynolds numbers, then it went to a constant value between about 4000 and 2 into 10 power 5, after which it once again the drag once again decreased at the drag crisis. In this case, since at high Reynolds number there is no boundary layer formation and wake formation and so on, you get a drag coefficient which goes as 1 over Re both at low Reynolds number as well as at high Reynolds number. Okay. So, for real bubbles, what is the parameter regime for which the Reynolds number is low and for which the Reynolds number is high? Okay. So, let us analyze that. Okay. So, example, okay. Spherical bubble in water of density rho is equal to 10 power 3 1000 kg per meter cubed. Okay. Water density is about 1 gram per centimeter, which is 1000 kg per meter cubed, and viscosity 10 power minus 3. Okay. Kg per meter per second. Okay. So, that is the density and the viscosity of the water. Okay. And surface tension gamma is equal to 0.072. Okay. So, the question is, what bubble diameter and this is rising at its terminal velocity. Okay. What is the diameter for which Reynolds number is small and capillary number is small. Okay. So, we have to find out what is the diameter for which the Reynolds number is small and the capillary number is small. First of all, we have to determine what is the drag force, okay, for the low Reynolds number regime. Recall that CD is equal to the drag force by the projected area, okay, by d square by 4 divided by rho times the terminal velocity square by 2. Okay. This is equal to 16 by Re is equal to 16 by and you can just do some simple algebra to get the drag force is equal to 2 pi mu d Vt. Okay. Solid particle it was 3 pi, in this case it is 2 pi because the drag coefficient of solid particle was 24 by Re, in this case it is 16 by Re. What is the force balance equation for a rising bubble? Okay. The gravitational force is equal to the drag force. Okay. So, Fd is equal to, in this case it is the buoyancy force because the density of the gas bubble is much smaller than the density of the liquid. Density of air I told you is about 1.25 kg per meter cubed. Liquid is about 10 power 3. So, we can neglect the liquid the gas density comparable to the in comparison to the liquid density. Okay. So, this is equal to mass of liquid displaced times g. Okay. mass of the liquid displaced is equal to density of liquid into pi d cubed by 6 times g. Okay. And this is equal to 2 pi mu d Vt. This implies that the terminal velocity is equal to rho g d square by 12 mu. Rho g d square by 12 mu is the terminal velocity, okay, just by solving this equation. Okay. The Reynolds number is equal to rho Vt d by mu is equal to rho g, I am sorry, into that is the terminal velocity into rho d by mu. Okay. So, this is equal to rho square d cubed, I missed a factor of g somewhere. So, let me just put that in, rho g d square. G by 12 mu square. Okay. So, this is what is called the Archimedes number by 12, okay, where the Archimedes number is a dimensionless number, rho square g d cubed by mu square. Okay. It should actually be the density difference between the liquid and the gas, but because we have neglected the density of the gas, this is just the Archimedes number. Okay. So, the Reynolds number is small compared to 1 for Archimedes number by 12 much less than 1, okay, which implies that rho square g d cubed by mu square very much less than 12. Okay. Or d is very much less than 12 mu square by rho square g whole power 1/3, okay, which is approximately equal to 1.06 into 10 power minus 4 meters. Okay. If you substitute the values of the viscosity of 10 power minus 3 kg per meter per second, density as 1000 and the gravitational acceleration as 10 meters per second square. So, when the diameter is less than about 0.1 micron of the bubble, then viscous forces are dominant. We had also asked the condition in which the capillary forces are, capillary number is small. Okay. Recall that the capillary number is defined as mu Vt by the surface tension, ratio of viscous and capillary and surface tension forces. When the capillary number is small, surface tension forces are much larger than the viscous forces, and you can neglect viscous forces comparison to surface tension forces, and in this case the bubble is approximately spherical, okay, when the capillary number is large. Okay. So, based upon this terminal velocity, I can write mu by gamma into rho g d square by 12 mu, okay, which is rho g d square by 12 gamma, okay, which if you recall is the Bond number by 12. Okay, so, the capillary number for a rising bubble is 1/12th of the Bond number, and the capillary number is much smaller than 1. Okay. Capillary number is much smaller than 1 implies that rho g d square by 12 gamma is much smaller than 1, which implies that d is much less than root of 12 gamma by rho g, which in this case is approximately 9.2 into 10 power minus 3 meters. Okay. So, for bubbles with less than about 9 millimeters, okay, close to a centimeter, the capillary number is small. Okay. So, you can effectively neglect the deformation of the bubble due to the viscous stresses, because viscous forces are much smaller than capillary forces. And less than about a millimeter, the viscous forces are dominant and inertial forces can be neglected. So, this is how we can incorporate, we can estimate using the correlations, the values of the Reynolds and the capillary number for real bubbles, and identify domains in which the Reynolds number is small. So, viscous effects can be neglected and the capillary number is small. Okay. So, to summarize, for bubbles we can neglect the density within the bubble. There is a zero stress condition at the surface, because of which there is no separation of boundary layer and so on. For a laminar flow at low Reynolds number, the drag coefficient is 16 by Re. For a turbulent flow, it is 48 by Re. In both cases, these correlations apply only if the bubble surface is clean, in which case you can apply a zero stress condition. If there are molecules on the surface which tend to increase the surface tension and make the surface rigid, then you cannot apply these. It will be similar to what we had for a particle. In the case of a clean interface, where a zero shear stress condition applies, the drag coefficient is 16 by Re for the flow around a bubble at low Reynolds number and 3 times that at high Reynolds number. So, I have completed the discussion of flow around a particle, flow around a bubble. Next class, I will start looking at flow through a packed column, through the interstitial spaces. I will continue that in the next lecture. I will see you then.